Okay. All right, so section 5.3, we are now going to learn about the logarithmic functions, which, like I mentioned before, they are the inverses of the exponential functions that we just learned about. So on these two graphs here, and I'm going to talk about what a log function is, but I just wanted to kind of show you the two graphs here. The ones in gray are the ones we learned about for the exponential functions. So this one is the exponential function a to the x that we were just doing when a is greater than 1. And that one goes through that point, 0, 1. And then the one in red on that graph is the logarithmic function when and here's the form of it, log base a of x. So I'm going to talk about what that means. But the base a will be this graph in red if that base is positive. So for an example of what a logarithmic function would look like, could be f of x equals base 3 of x. So this has a base 3 and it's positive. So that's what the graph will look like. And this one will go through the point 1, 0. And so you can kind of see that those are inverses of each other because they are reflection over that line y equals x. So I'm just kind of showing you visually right now that they are reflections. Nothing, I'm going to go over these properties more. And then the other one is when a is between 0 and 1. So the first one here is the exponential, the one that was decreasing and going through the point 0, 1. And then the other one is for the log function. And it would be also decreasing from left to right. And it goes through the point 1, 0. Okay, but what is a log? And let me give you an example of this graph for the log. Could be like log base 1/2 of x. So first of all, the base there for a is always going to be written like smaller, and that's called a subscript. So you'll always see it written like smaller, like down a little bit, like that 3 is, or this 1/2 is. It's called a subscript, so that's just a notation. It's kind of the opposite of an exponent. Instead of being up high, it's like down low. Okay, but that's just so that you will recognize what the base is. The base will always be that a number. Just a little subscript. Okay, so what is a log function? So this says that we define y equals log base a of x, which is how I read that, log base a of x, as the number y such that x is equal to that base a raised to the exponent of y. So this, when it's in this form over here, that y is the exponent that I need to raise the base a to in order to get the x, which is in the function. So for example, if I had y equals log base 3 of 9, up here, this is asking what is the exponent, which is the y, that 3 needs to be raised to in order to get 9. And that would be 2, right? 3 squared is how we get 9. So y would be equal to 2. And I could also say that log base 3 of 9 is equal to 2. Because that's the exponent I need to raise that base of 3 to in order to get 9. Okay? So that's what a log function is. It's really equal to an exponent. Again, the exponent that you need to raise your base to in order to get what's inside your log function. All right, so for these, whatever's inside the log function will be greater than 0. So anything that's inside of that log function. And this doesn't mean log base a times x. That x is like inside of that function. Just like when we had radicals, if I had the square root of x minus 2 is contained under that radical. So if I had log base 3 of x minus 2 is contained in that log. It's inside of that function. So the log is like its own operator. Okay, and I'm going to talk about that more in a second. Yeah, but it has to be positive because I forgot what I was kind of saying. Because we are also going to assume that all the a is positive, all the bases. We're only going to consider positive bases for log functions. For any type of log function, you will never see a negative base. So if I have a negative base, or I'm sorry, a positive base, like this 3 here, the base will always be positive. Well, there's no exponent that I can raise it to that will give me a negative number, because it's positive. So if I take a positive number and I square it or cube it or raise it to the 4th, it'll always be positive. So we're only considering all the positive cases with log functions, okay? All right. Any questions so far? Good? Okay. So let's talk about some properties of these log functions. And again, I'm going to come back to their graphs and their properties a little bit later. But we are going to talk about some properties first. There is a lot of properties of logarithmic functions. And in section 5.3, I'm only going to really be going over half of them. Section 5.4 is all about properties of logarithms. So there's a lot. But the first property here is really, I've kind of already said it. It's kind of contained in its definition that I went over up here. But it's how we can get from logarithmic form, which is right here, to its exponential form, which is right here. So if we have an equation like this, and it's logarithmic form, log base a of x is equal to y, I can rewrite that into an exponential form because the log is an exponent. So I just take the base a and then I raise it to the power of y, because what the log is equal to is always the exponent. And then I have to go back over the equal sign, and it's equal to the x. So I always used that like counterclockwise method with my arrows when I was doing these. It just helped me remember how to go back and forth. But also you can have this on your cheat sheet. So And there's that. Let me show you an example. If I had log base 5 of 7 equals to x. This is in logarithmic form. So if I wanted to transform it to its exponential form or rewrite it in its exponential form, then I start with my base, which is 5. You always start with the base. And that base will become the base of your exponent. So that's pretty convenient. And then you have to go down and up and raise it to the exponent of x, whatever that log function's equal to. Then you have to go back over the equal sign, and it's equal to what's inside the log function, which is 7. So that is its exponential form. And then you can go backwards too, like they'll give you the exponential form, and then you just need to plug all that information into the log, which we're going to do some examples in a minute. Okay, the next property says that anytime we have log base anything, it doesn't matter what a is, if 1 is inside the log function, then this is always going to be equal to 0. And that's true because anything to the 0 exponent is equal to 1. That's the only thing that would make it equal to 1. Unless a was 1, but a is not going to be equal to 1 because it says it's a positive constant other than 1. Because 1 to any exponent is just 1. So we're definitely not worried about that. So a will not be 1. So again, if I transformed this equation here to its exponential form, I start with that base a, it gets raised to the exponent of 0, and then it's equal to 1. Well, that's true because anything to the 0 power is 1. So if you have 1 inside of the log, that will always be equal to 0. So an example would be log base 4 of 1. This would just be equal to 0. Log base x of 1, this would just be equal to 0. As long as 1 is the inside of that log function, it'll be equal to 0. And then the next property is whenever the base and then the expression inside the log function, if those match like these do, a and a, then this will just be equal to 1 because a, which is my base in this case, to the 1 exponent is just itself. So when those match, that will just be equal to 1 because that's the only exponent that will give you back itself. So example, if I have log base 5 of 5, this is just equal to 1. If I have log base 1/2 of 1/2, this is just equal to 1. Anytime those match, the subscript and then the number inside of the log function. All right, and then this last property says that the domain of a logarithmic function consists of all numbers x except for any values of x that makes the expression inside the logarithmic less than or equal to 0. So I already told you from this up here that the x inside the log has to be greater than 0, strictly greater. It cannot equal 0 either, because no exponent will result in something being equal to 0, unless a was 0, but it's not. So for example, if I had log base 3 of x minus 2, and let me write it as a function, because that's what that is. Okay, so if I had this function log base 3 of x minus 2, first of all, if there is more than just a number or more than one term in the log function, they'll usually put that in parentheses for you so that you know all of that is being contained in my log function. And so all of that needs to be greater than 0. We cannot take the log of anything 0 or negative. So to find the domain of this, I would need to set x minus 2 greater than 0 and solve for x. So I would add 2 to both sides of that inequality. So x would have to be greater than 2. And this would be the domain. Has to be greater than 2, or that expression in there will be equal to 0 or negative. So it's kind of combining the rules for radicals and rationals. So now it can't be 0 or negative. Okay. All right. So let's just do a couple of these examples here so that we can get familiar with what a log is. So in Pearson, they're going to ask you questions like this. So we are using the definition of logarithms to find the following logarithmic values. Okay, so zoom in a little bit. For a, this is log base 10 of 10,000. So again, this is asking me what exponent do I need to raise that base of 10 to? So like I could do 10 question mark with the exponent for it to equal 10,000. Anybody know?
105?
Close. 4. 10 to the 4th power is 10,000. So if you didn't know that, you could just start taking that 10 and raising it to exponents in your calculator, or powers of 10. When you raise 10, like for example, if I take 10 and I square it, what's 10 squared? 100. Notice there's 2 zeros here. What's 10 cubed? 1,000. Notice there's 3 zeros. 10 to the 4th has 4 zeros. 10,000. 10 to the 5th has 5 zeros. 4, 5. So every time you raise it to a higher number, it just adds another 0 to it. So that's one way you can kind of remember that. Or you could just do your calculator. So this one in particular would be equal to 4. Yes, or this whole thing equals 4. But you're not wrong about, I'm about to use that technique and set them equal to a variable y, and then we'll say y equals. But you won't have to put in Pearson y equals, it'll just be the number that it's equal to. All right, so that's a little side note there. All right, let's go to B. B is a little trickier. So, here's where in the class it starts like you really have to think about everything we've learned, okay? You have like a toolbox now, hopefully, of things I've taught you and that you've learned. And you kind of have to start piecing it all together with these types of problems. So for this one, I am going to just set this equal to some unknown variable because I don't know what it's equal to right now. And then I'm going to transform it into its exponential form. So I start with the base of 10, and it gets raised to that unknown exponent of y. And then it would be equal to 0.01. So I'm trying to figure out what do I need to raise 10 to get it to equal 0.01. So whenever it's equal to a decimal like this, you want to, well, your end goal for all of these is to try to rewrite this side as a power of 10. But to rewrite it as a power of 10 when it's a decimal, this needs to be turned into a fraction. So maybe you remember how to write 0.01 as a fraction. If you don't, your calculator will do that for you. If you type in 0.01 in your fraction and then hit math fraction, it'll put it into a fraction for you. But to do it by hand, to write a decimal as a fraction, you just take the number, which the only number here is 1. That 1 is in the hundredths place. So I take that 1 and I put it over 100. So another example of that, if I had 0.234, the 4, the last digit, is in the thousandths place. So I take that entire number, 234, and I put it over 1,000. So that's how you write decimals as fractions. But again, your calculator will do that. Okay, so now 100 can be written, I'm going to rewrite this up here, 10 to the y power equals, 100 can be written as a power of 10, like we just seen, as 10 squared, right? 10 squared is 100. And because it's in the bottom of the fraction, how would I rewrite that? Using a negative exponent. Anybody remember? Exactly, 10 to the negative 2 power. So that comes from that rule. X to the negative n power is equal to 1 over x to the positive n. We learned about this. And so therefore, y would have to be equal to negative 2. Or that log expression would be equal to negative 2. Now, as we go on today, later on, I am going to show you how to type this whole thing in your calculator. And then it'll give you the answer. But we need to learn why we're doing these things. All right. C is a little bit easier. So what would I have to raise 5 to for it to equal 125? Anybody know? 3. So this is just equal to 3 because 5 cubed is equal to 125. So again, to figure that out, you would just start with 5 and start raising it to different exponents. D is also a little bit trickier. So D is saying, what do I need to raise 9 to get it to be 3? Well, now we're getting smaller, right? And this is not a decimal, so how do we figure that out? Well, I'm going to do the same thing. I'll set this equal to y. And then I will transform it to its exponential form. So I'll start with the 9 and raise it to the exponent of y. And then that will be equal to 3. So whenever this number inside the log is smaller than your base, then you need to think about fraction exponents. Okay, so let me just skip to kind of what I'm trying to say. The square root of 9 is equal to 3, right? Mm-hmm. And do we remember what exponent the square root is?
2.
Close. That's the root of it. But as an exponent, how would I rewrite this? 1/2. So y would be equal to 1/2. So this rule is very important. You'll be seeing this a lot. So I'm going to rewrite it up here to remind you of that rule. If I have the nth root of x to the m power, this is equal to x to the m divided by n exponent. So you will be seeing that a lot in this section. So that one was equal to 1/2. Couple of examples of that, like the cube root of x is equal to x to the 1/3. The fourth root is equal to x to the 1/4, and so forth. Okay, E is log base 6 of 1. Remember what this is equal to? 0. Log base 6 of 1 is just 0 because of that property right there. And then F, log base 5 of 5, well, those two match. So this one's just equal to 1. Okay. So the next thing we're going to do is work more with converting from logarithmic to exponential and exponential to logarithmic. So for this first, for number 2 here, we are converting each of these into logarithmic form. So now they're giving us the exponential form. And they're wanting us to go to logarithmic form, which is this. So this is the formulas that I went over on the previous pages. This is exponential, and this is logarithmic. So same thing we were doing. So same thing, if they give you, the exponential form, and you need to go to logarithmic form, you are always going to start with the base, just like I said last time. So the base in this problem is 2. And so to start, I would write log base 2, because that will be the base of my log. And then the exponent is always what this is equal to. Remember, the log is always equal to an exponent. So the x, which is the exponent in this exponential form, will be oh, I'm sorry, I'm getting mixed up here. I wrote this wrong. Sorry. Well, that part was right, but I wrote my formula down wrong. This should be like this. My apologies. So the exponent in my problem, 2 to the x, is actually the y here. That's the exponent. So that's what this will be equal to, like I said. And then whatever the exponential is equal to, that's what goes inside your log function. Okay, so the next one, the base is equal to 10. So this will become log base 10. That needs to be the base of my log. Thank you. And then I know that the log is always equal to the exponent, which is -3. And whatever the exponential is equal to, that's what goes inside of your log. Okay. All right, C, remember we talked about what E was, which is just a number that's approximately equal to 2.714, I think. So that's just a number, so don't let that throw you off. We're just going to use E. And E is my base. So I start with log base E, and this will always be equal to the exponent of T, and then the 70 will go on the inside. So that will be the answer. Now, when they are asking you to convert to, one of these forms, logarithmic or exponential, they don't want you to solve anything. Like, they don't want you to simplify. I mean, unless they told you to simplify, but right now in this section, you should just be entering these as your answer. Like, I can figure out what I need to raise 2 to get to 16, but that's not what they want me to do. They just want me to enter this, because they just want me to rewrite it as its logarithmic form. Okay, so that was going backwards. So now 3, which we've already kind of done some of these, is going from logarithmic to exponential. So I think these are a little bit easier. But for these, you're going to start with your base, which is, in this case, 2. And then you go down and up. This gets raised to the exponent of 5. And then it is equal to 32. And that's a true statement, so that's how you know you did it right. Then the other one would be what? What would B be? Perfect. A to the power of 8 equals Q. And then the last one, sometimes they'll switch the order on you, but you're still doing the same thing. And what I mean by order, now they have the log written on the right side of this equation, but it's still, the base is T, and this will be raised to the power of X, and then it'll be equal to M. And you can rewrite it if you need to, if it helps. Putting the log function on the left and setting it equal to that X. All right. Good so far? Okay. Okay, the next two things, these next two boxes are like really commonly used. I should say frequently used, because the first one is called common. Frequently used logarithms. So before we had calculators, mathematicians had to mainly rely on these common logarithms here. And to be honest, the other type of logarithms, the regular, well, actually, let me say that in a second so you know what I'm talking about. So a common logarithm is whenever the base is equal to 10. So this is the most commonly used logarithm, when the base is 10, because that's because we have a base 10 number system. Every time we count, if we count by tens, everything starts over each time we count by 10, like 10, 11, 12, 20, 21, 22, 30, 31, 32. So that's our base system, number system, base 10. So that's the easiest number to work with these logarithms. So because they're so common, we actually don't even write the base for these. So you're gonna see in Pearson that they'll give you stuff like this without a base. And if you don't see a base, a subscript, it's understood to be base 10, okay? So log of 3 is equal to log base 10 of 3. So anytime you don't see the little subscript, it is understood to be 10. So that's the common log. And this one is the log button that's in your calculator. So if I switch to the calculator, yay, it followed me. You see this log button down here by the number 7. If I click on that, it gives me this log expression in the calculator. This log in your calculator is just base 10. That's it. That's the base that it is. So if I type in that one problem we had earlier, 10,000, this means log base 10 of 10,000. I'll close my parentheses, and we said that that was equal to 4. So if I hit enter, that's equal to 4. Okay, but now, so just recently, like very recent, they added, this was the only log function in your calculator. You could only enter in a base 10 for logs in your calculator. So like very recently did they just add a feature, and I'm pretty sure even like the TI-83s don't have this feature right now, just the TI-84s. I had someone with a TI-83 and they didn't even have what I'm about to show you. But if you do have a TI-83, then I can show you how to do it in your calculator still. We're going to still learn that. But to enter in any other base for a log, you go and you click on this math button. And then you scroll down to where it says log base. So we do have that now in these TI-84s. So if I hit enter, now it looks like this. So it allows me to enter any base I want to. So that one example we had, base, come on, base 5 of 125 was equal to 3, right? So if I hit enter, that gave me 3. So I can actually enter in whatever I want. And if I do math, and then I go down to log base, and I put that one problem, 9. Trying to remember what it was. 9 of 3. This was equal to 1/2. And it gave me 0.5, which is 1/2. Okay? So a lot of your homework problems you can just do with your calculator. All right. So that is that. The other most frequently used log is the natural log. So this is whenever the log has a base e. So log base e of x. But we don't usually write it like this. If it has a base e, it's written like this. ln of x. And that's how we say that. So anytime you see ln of x, this is the same thing as log base e of x. Or ln of 3, this is the same thing as log base e of 3. But we just don't write it with the log because it's kind of like abbreviated, ln. ln for natural log, except for it's kind of backwards. Okay, so why are these frequently used? Because again, they kind of model things in nature. So that E number models things in nature. So do these natural logs. So these are two rules that you should definitely be aware of. ln of 1 is equal to 0. Well, that's the same rule we already learned, really. Anytime 1 is inside any log function, it's equal to 0. So that's equal to 0. And ln of e is equal to 1 because ln of e is equal to log base e of e, which is 1 because those match. Okay. So if I go back to my calculator, there is a ln button right below the log button, right there. And if I type second e, this will just be equal to 1. And remember I said you can never put 0 or anything negative into a log. So if I tried to do ln of -4, this will give me an error. Can't do it. If I tried to do log of -4, that will give me an error as well. Can't do it. Also, log of 0. I can't do that. Error. Or ln of 0. I can't do that. So, just shows you that it's not on the graph. It's not in the domain. All right, so let's go back. Okay, so those are those two logs. Now, this next part is the change of base formula. So this is what they used before they put that feature in the calculator. So it is a way that you can enter these in your calculator if you don't have that log base feature. And it's by using this change of base formula, which allows us to convert any log into this fraction here using any base we want. So this formula says that for any logarithmic bases a and b and any positive number m, log base b of m is equal to log base a of m divided by log base a of b. And this b should be a lowercase b. So it matches exactly, just for some reason, to capital B. Should be a lowercase b. It's the same b you see over there. I'll rewrite it. Log base b of m is equal to log base a of m over log base a of b. So this is taking what's inside the log of the original and putting it inside the log of the numerator, but I'm changing the base to whatever base I want. So now that little base from b is equal to a. But then I divide that by that log base a, whatever the base I chose, and then I put the original base, which was b, inside of that log function on the bottom. So usually when we do this, we will choose a log base 10 because that's the common log, or the ln because both of those can be put into our calculator. So for example, number 1 says find log base 5 of 8 using common logarithms. So common logarithms is whenever the base is 10. That's what I just said. Log base 10 of x is a common logarithm, which is the same thing as just log of x. We don't usually write it if the base is 10. So this will become log of 8 over log of 5. And again, both of those have base 10s. So then I can easily put this in my calculator. So let me go back. So I would hit the log button here, which is log base 10. So log of 8, but you want to close your parentheses or you'll get it wrong. Divided by log, what was it, 5? Log base 5. So I hit enter, and it gives me 1.2920 blah blah. Now if you have that log base feature, then I could have just put the original, which was math log base. 5 was my base and 8 was my inside of my log. Hit enter, I get the same answer. So it's the same thing. I could have also used the natural log for my change of base. So that would have been the natural log of 8 divided by the natural log of 5 instead of using the log. This will still give me the same answer. So that's 3 different ways you could have found the value of that log. Make sure you close your parentheses though. So I already forget what did that say? 1.292. I'll round it to 1.292. All right, so the next one is log base 3 of 7, and it wants me to find this using the natural logarithm. So now I'm going to use the ln. So again, I take the ln of, I'm going to say ln of the bigger number, but when I say bigger, I mean the one that the font is bigger, not like the value is bigger. 7 is the font, it's written larger. So you take the ln of the larger written number and divide it by the ln of the base, which is 3. And again, like I just showed you, this would be the same thing as log of 7 over log of 3, or you could type this in your calculator. But they're just telling me to use the natural logs here. So now I'll go back, and this will be the natural log of 7, close my parentheses, divided by the natural log of 3. And that gave me 1.771. I'll round it to. Okay. Good. Need help? Good. All right, so last part of this section is about graphing these functions. So now I'm going to go a little bit more in depth about their graphs again. So I'm going to redraw them here for you. So these are the base graphs you can add to your cheat sheet. And I told you guys you could have a full piece of paper for your final exam. You can have a full piece of paper instead of just a flashcard.
I gotta rewrite this again.
Hey, the more you rewrite it, the more it helps you retain it.
You're right.
So, but still no worked out examples, just formulas and notes. Okay. So you can add these graphs. So the basic graph, the basic form of a logarithmic graph is log base a of x. That's our base graph. So if that a is greater than 1, it will look like this. And it'll go through the point 1, 0. And for our exponential functions, our graph had a horizontal asymptote, right? Remember that at y equals 0? Well, these will have a vertical asymptote at x equals 0. And that'll always be true for the base graph. And then so it'll never cross that vertical line. And if a is greater than 1, it's still increasing. So that didn't change. It's increasing over its domain. But its domain here would start at 0 with a parentheses because it would never touch x is 0, and it would go towards the right to positive infinity. Okay. The other one is when the base is between 1 and 0, so like a fraction. So that one will look like this. So it'll be decreasing. It'll still go through the point 1, 0. It'll still have a vertical asymptote. At x equals 0, so that it'll never cross. And the domain will still be from 0 to positive infinity with the parentheses because it can't equal 0. So all of that you can have on your cheat sheet for your base graphs. Okay? All right. So let's graph number 1. Number 1 is going to be pretty easy because it's just, there's no transformations happening to it. It's just log base 5 of x. So this will be in this shape here because the base 5 is greater than 1. And there's no transformations. There's nothing being added anywhere. There's no negatives, nothing else. So I know that this base graph will definitely go through the point 1, 0. And that's because if I plugged 1 in here, then it would be log base 5 of 1. We learned that this is always equal to 0. If 1 is in the log function, it's equal to 0. So that gave me the point 1, 0. That's why these will always cross through that point. And I can find another point if I want to, but again, you just seen me do, well, not the online class, but for y'all, you seen me show you how to graph the exponential functions. You always start with the base graph and then you're just entering your transformations. So we don't even really need to find another point if we're doing it online, but it's definitely useful to know because sometimes they'll give you those multiple choice graphs and maybe you need to narrow it down and make sure your points are lining up. So if I wanted to find another point on this graph, the easiest number to plug in for x would be 5 because that matches my base. And I know that log base 5 of 5 is equal to what? 1. Perfect. So this would be equal to 5, 1, which would be right here. So I know that it's looking like this. Yeah. Okay. But again, I'm going to go back to Pearson and show you that you really don't even need to do that on Pearson. You just using your transformations for graphs like these. So instead of doing these here, I am going to go into Pearson and we're going to do some more in Pearson and then we will take our break. So that would be the graph of number 1. So let me try to pull up Pearson here. Okay, we'll do this one. Okay, so it says for the following function, briefly describe how the graph can be obtained from the graph of a basic logarithmic function, then graph the function and state the domain and the vertical asymptote of the function. All right, so with this one, even with the ln, the log functions, we need to always start with the base graph. So in this case, the base graph would be ln of x. And ln of x is the same thing as log base e of x, right? And e is greater than 1. So this first case is when a is greater than 1. So again, ln of x is equal to log base e of x. That's what we just learned. So the base e, which is approximately equal to 2.17 or 2.714, is greater than 1. So it's still in this case. And for log, it would look like this, where it goes to the point 1, 0, and the vertical asymptote is equal to x equals 0. That's our base graph. And then the negative in front of that ln of x would be a reflection over the x-axis, because it's a negative in front of the entire graph. So reflection across the x-axis. And then the 6 is being added to the negative ln of x, because in front of it is positive, right? So that would be a translation up 6 units. Okay, great. So I'm going to hit click to enlarge the graph. And then again, I'm going to start with the basic shape of the base graph, which is this one. So it would look like this, where it's increasing since e is greater than 1. And then I'm going to plot the point that I know it goes through, which is 1, 0. And then I am going to do my transformations, but it won't let me. What was it? 6 minus ln of x. So I will do the reflection. So you can see here that the base is already e down in that little box, so you don't need to change that. And it's not letting me move this, that's why. Oh. Yeah, it's not letting me move it because it's on my iPad. But the negative in front of that ln of x was a reflection over the x-axis, so I'm going to click on that. And then it's a vertical shift up 6 units. It's not showing me that. Oh, okay, here we go. 6, okay. So you move the vertical shift to positive 6. Save it. Okay, great. So again, you just have to start with the base graph and then enter in your transformations. Okay, now on these, it's going to ask about the domain. So remember we said the domain of the base graph is from 0 to infinity because it'll never cross that vertical asymptote. Well, unless we move this left or right, that will always be the same. Okay? If I move it up and down, that's not going to change. If I reflect it, it's not going to change. The only thing that will change that domain and that vertical asymptote is if you have a horizontal shift. So my domain here is still going to be parentheses 0 to infinity. Like that. With a parentheses on the 0 because it cannot equal 0. And then the vertical asymptote's not going to change either. That will still be x is equal to 0. Because I didn't have any horizontal shift. Okay, let's do one more and we'll take a break. So this one is 1/4 times log of x minus 5 and then minus 7 on the outside. So what's my base here? No. Do you see one? It's 10. Because if it's written as log and then there's no little subscript, it's understood to be 10. That's our common log base 10. So it will look like this. You're right about that because 10 is still greater than 1. So this will be our base graph here. So it says shift the graph of y equals log of x, which again is the same thing as log base 10. And it's saying down or up, so which one would that be? Down, because of the minus 7. That's what's being subtracted on the outside. Okay, and then so many units blank. So this is talking about the horizontal shift, which is the minus 5. And because it's horizontal, it's always backwards. So if it's subtracting, it's going to go to the right. And that will be 5 there. Okay, and then the 1/4. So the 1/4 is a constant being multiplied in front of my base graph, in front of my log function. So anytime you have a constant being multiplied in front or to the entire base graph, that is a vertical stretch or compression or shrink. Compression means shrink. And because it's a fraction, that will be a vertical shrink. So that one would be shrink it vertically. But again, you can have that little note card for all of that. So check it. Great job. All right. So for this one, we're going to choose the base graph, which would be the one that's increasing from left to right since the base was 10. So that would be that one there. And then I'm going to plot the point 1, 0. That's not right. Wait, I'm sorry. I said that wrong. I need to click this one. They're actually both increasing, but the one on the left is the one for the log function. So I need to click that one, and that goes through the point 1, 0. And then, I already forget, we will do the horizontal shift first, which is the -5. So that'll go to the right. So I actually need to go to +5. So it'll move it to the right 5 units. And then I'll do the 1/4, which is a vertical shrink. So I need to move this to the decimal equivalent of 1/4, which is 0.25. And then I had a vertical shift down 7 units. So that'll look like that. The base is already base 10, which is what it should be because it was just a log, regular log. So I'll save, check, and that's correct. All right, so the domain. So if this was my base graph, and then I shifted it to the right 5 units, then my vertical asymptote, which was originally x is 0, would also be shifted 5 units. So that'll become x equals 5. Make sense? So you can kind of see here that it's in between 4 and 6 where my graph is kind of stopping. So the domain will be from 5 to infinity now. It's whatever you had to shift it. If we shifted it to the left, it would be -5 because it would be shifted to -5. And that would be also the equation of my vertical asymptote now would be x equals 5. Because that all got shifted. Okay? So we will take a short break.